Okay, we're going to take a little bit of time and go through the homework problems for the independent samples tests. So let's take a look at this. Homework problems. You can find all of this information if you go to, let's go to Unit 4. And overview, you can download the independent samples worksheet, or you can go to independent samples and download the independent samples worksheet here. Another thing that you're going to want is go to printable resources, and you're probably going to want the hypothesis testing decision tree. So we're going to download that, and then the critical values diagram. So let's download that, and then we also might need the t-chart. That should be all that we need. So I'm going to have those down at the bottom. Actually, I'll open them up just so I can have them up and ready to go. So those are the three documents that you will most likely need. And so we'll open those and have those available. So let's go ahead and get started with the worksheet though. So this is this right here is a problem from the book. And let's take a look at it. The known standard deviation in a salary for all mid-level professionals in the financial industry is $11,000. So what I like to do is, as I go through things, I like to make notes of what it is that I'm looking at. So I'm going to just make a few notes. The known standard deviation in the salary of mid-level professionals is $11,000. So I'm going to highlight that, and I'm going to do insert. I'm going to pin that, and then I'm going to do review, new comment, and then pop SD. So I've got the population standard deviation, and then company A and company B are in the financial industry. So what we have here is we have population 1, and then right here we have population 2 are in the financial industry. Suppose samples are taken of the mid-level professional company from company A and from company B. The sample mean for every salary for mid-level professionals in company A is $80,000. Okay, so what we have right here is mean for population 1 is 80,000. Okay, and then let's come up here. The standard deviation, what is it? $11,000. Okay, $11,000. The sample salary for mid-level professional company B is $96,000. Okay, so let's highlight this. New comment. Mean for population 2 is $96,000. Company A and Company B management want to know if their mid-level professionals are paid differently on average. Okay, so what is it that we want to know? We want to know, are they different on average? New comment. What we want to know is whether or not these companies pay differently on average. Okay, so it's just a really good process to go through and just highlight and note what it is that you're looking at. Okay, so let's look over here. Let's take a minute and make sure we know what test we're running and why. So what you need to do is pull out the hypothesis testing decision tree. Okay, so pull out the hypothesis decision tree, and this was something that you were able to download off of Canvas. And now we're going to follow this and say first, is this dealing with continuous data or is this comparing frequencies? And if you look at this, at the very top, you've got two questions. Are you dealing with frequencies, or this right here is continuous data from samples or a population, and then this over here is dealing with frequencies. And so we know that we are dealing with continuous data because we've got company A and company B with the, what is it that we're even looking at? The sample mean salary, the mean for the mean salaries for two different companies. So that's continuous data, and we're looking at their means. Okay, so the next question is, are you examining the difference between groups or between a sample and a population? And so we are looking, and right here you'll see on the decision tree, it says, because we went to the left-hand side, so let's highlight this and say, okay, this is where we went. The next, am I examining the difference between a sample and a population, or am I examining the differences between groups? And the answer is, we're looking between company A and company B, so therefore we're looking between groups. In other words, the same exact person, do you have two scores for the same exact person, or for the same exact, observable linked record? If you do, then you compare those responses together. But if all that you have is the mean of group 1 compared to the mean of group 2, and there's no way to pair them up, then independent is the way to go. So you say yes or no, and the answer is no. They are not being, the same participant is not being sampled more than once. They're only being sampled once. And so we're comparing one group to another group. The next question is the number of groups. If we have more than two, then you would do something else. But since we only have two groups, what we're going to do is the independent samples test. And so down here you can see this is the fun little path that I took. And it brought me to the independent samples test. And it will bring me through this all the way down. Now, we have, we'll go back to this. We're going to follow the 6-step process, and the way that we're going to follow the 6-step process, which is also outlined right here, but we're going to follow this 6-step process on this fun little sheet right here. Okay, first of all, what is it that I want to know? I already wrote this out. What do we want to know? We want to know whether or not the companies pay different on average. Okay, so we're going to put that right there. Okay, next, what is the null and alternative hypothesis? Okay, in order to find how to write the null and alternative hypothesis, this is a little bit different than the single sample test. Okay, with the single sample test, we were comparing a sample to a mean, but this time we're comparing a mean of a population to, or sorry, we compared a sample to a population. Now we're comparing a population to a population. Mu1 is less than or equal to, greater than or equal to mu2. In other words, sample 1, let's do this, Control C, Control V, and then Control C, Control V. So, and let's make this subscript, home, font, subscript, and press OK. So we've got mu1 is less than or equal to, what is it that we want to know? What we want to know is, are they different? Are they different? And so if we want to know are they different, then we know that it is a two-tailed test, and that the null hypothesis is going to be that there is no difference between the two. There's no direction at all. It just says, are they different? And then the alternative hypothesis is going to say that there is a difference. Okay, and you can write this a few different ways. You can write it A and B, because we're dealing with company A and B. So if you do mu sub A is equal to mu sub B for hypothesis, for the null hypothesis. And what does this mean? What this means is there is no difference between how much company A pays compared to company B. And then the next one for the alternative hypothesis, saying that there is a difference. There is a difference between how much company A pays compared to company B. Okay, so the next question is, what is the level of significance, or the alpha level, or the probability of committing type 1 error? So coming back up here, I don't know if it says what it is. that it has. So sometimes you just have to choose. So what we're going to do is we're going to say, you know what, we're going to choose with only a 5% chance of saying there is a difference when there really is not a difference. So we'll save that, and I'll save that and upload it. But so that right there is, there's a 5% chance saying that there is a difference when there really is not a difference. And so the level of significance is going to be 0.05. Okay, what is a test statistic? Well, the test statistic, the way that we determine what the test statistic is whether or not we have the population standard deviation. If we have the population standard deviation, then it's going to be z. If we don't, then it's going to be t. So the known standard deviation, in other words, the population standard deviation, is 11,000. Because we have the population standard deviation, the test score, or the test statistic, is going to be z. Next, what is the decision rule? Okay, so the decision rule is, we're going to pull something out really quick. The decision rule, we've got the critical value diagram, and this is a two-tailed test. And you notice I have these decision rules literally written out, and so for a two-tailed test, it's almost always going to follow this exact setup. For one-tail upper, it's going to follow this setup. For a one-tail lower, it's going to follow this setup. So just follow it right along. So the decision rule is, for a two-tailed test, I'm just going to copy this, and I'm going to go back to here, and I'm going to say, okay. Decision rule is, reject the null hypothesis if, here we go, we're going to copy this. zcalc is less than negative 1.96, or if zcalc is greater than 1.96. And what we need to do is we need to make sure that we're using the right values. So basically what we're saying is reject the null hypothesis if the calculated value of your z statistic is less than the critical value, which brings us to our question of what is the critical value? Okay, what is the decision rule? What is the critical value? And I probably should have calculated it right here. What is the test statistic and critical value? So let's do z is the test statistic, and the critical value is, let's go to the critical value, with a 5% chance of type 1 error, it's going to be plus or minus 1.96. So let's just copy that. What is the critical value? Plus or minus 1.96. So we've got the critical value, and now we have the decision rule. So the decision rule is reject the null hypothesis if zcalc is less than negative 1.96, or if zcalc is greater than 1.96. Okay, and then fail to reject the null hypothesis. So fail to reject the null hypothesis if, we're just gonna copy and paste this, if zcalc is equal to or between negative 1.96 and 1.96. And so this is exactly how you would write it, and I'm going to show you really quick what this would look like. So we've got the decision rules. And so I'm going to put this right here. Okay, so this is I should have moved this out of the way. It says draw and label the critical values, test statistics, and p-values. Okay, so we're going to just put this right here. T-crit, so we're going to use z-crit. We're going to get rid of all the rest of them. Z-crit equals negative 1.96. And the reason why this is on both tails is because it is a two-tailed test. If it was a one-tailed test, it would only be on one tail. Okay, and then z-crit is 1.96. There we go. And then what we have here is the region of rejecting the null hypothesis. In other words, rejecting the region, if we have a z calculated value, if we have a z calculated value that is in the green area, anywhere in the green area, then we are going to reject the null hypothesis. If we have a z calculated that is anywhere in the middle, we are going to fail to reject the null hypothesis. And so what we're going to do is we are going to find the z calculated value. We're going to find the z calculated value and we're going to put it on this as well. So what is the z calculated value? Reject the null hypothesis. Okay, formulate your decision. We're going to compare the test critical to the test calculated, or you can compare the p-value to the alpha. Okay, if the probability of occurrence is less than the alpha, then it's significant. Just like if the calculated value is more extreme than the critical value, then it's also significant. And you can read through all of this. This is just more information that really tells you this is how you need to make your decision. Okay, and just sub in, instead of test, you need to put in, you know, chi-squared or z or t. Okay, so what is the value of test calculated? And we already have the value of test critical. So the critical value, we're just going to copy this, bring it down here. Critical value is plus or minus 1.96. And now that we've got the critical value, we need to look at the calculated value. And since we're dealing with the z-calc, there is a very particular formula for how to determine z-calc. And if you look right here, this is the formula for determining z-calc. There's once again a few different ways to write this. We can do it like this. Here, this right here is the standard error. The standard error for independent samples tests. And if you want to take a look at how to calculate the standard error for independent samples test, we can come to your textbook right here, the online textbook, and we've got the standard error for independent samples, where we have the standard deviation of the first sample plus the standard deviation of the second sample, or standard deviation over the size of n1, or the sample size, plus the standard deviation over the sample size of n2, and divided by, and taking the square root of that. Okay. However, in this case, we don't even have to do this, and the reason why is because the question already gives it to us, gives us the standard deviation of the companies, and the standard deviation of the companies is going to be 11,000. So it says standard deviation, or you can say standard error of, you know, it basically is treating it company by company. So let's do mu sub A minus mu sub B. So mu sub A is 80,000, and then mu sub B is 96,000. So that's going to be 80,000 minus 96,000. So that's going to be 16,000. And 16,000 divided by 11,000. So let's pull out our nifty calculator. And we're going to do 16,000 divided by 11,000. It gives us a z value of 1.455. Okay, so z equals 1.455. Oops, that's supposed to say equals 1.455. Okay, sorry, I've got 5. Okay, so we have our z-value of 1.455, and now we're going to calculate our p-value. But specifically, we need to know what is the probability of getting a z-score or of obtaining a z-score of 1.455 or more extreme. That's what the p-value is saying. What is the probability of getting this z-score or more extreme? So in order to be able to find that, there's two ways to go about doing this. One is to grab your trusty z-table, and if you go to your trusty z-table, we can go down to negative 1.4, and then go, negative 1.40, negative 1.41, 2, 3, 4, 5. And so it's going to be between between these two, so that's between 1.44, between 1.45 and 1.4, 1.46, and so it's probably going to be somewhere about 0.0731 or 0.073. So that's one way of doing it, is guessing, hey, what is it in the middle of there? But we do have another option. Like I said, we could put, point 0.073, or we can come over to Excel, to Trusty Excel, and we can use a formula. So the z-value, like what we had before, is 1.455, and so we're going to use a formula, and it's equals norm.s.dist, and we're going to put the z-value in there, and then we're going to put true for cumulative. So what this is going to do is this is going to give us the probability of a value occurring anywhere to the left of this z-value, because it's cumulative. It's everything from the farthest, or from, basically infinity that way, infinity to the left, all the way up to that z-calc value. So that's what this is giving you. It's giving you the left tail probability. But we need the right tail probability, and so in order to get the right tail probability, what we need to do is we need to do equals 1 minus the left tail probability, which is going to be 0.07285 or 835. So this right here is a probability of 1.455 or greater. So this is the right tail probability. However, we're still not quite done yet. Remember, this is a two-tailed test. So what we're looking for is, what is the probability of having a z-calc that's more extreme than 1.455? So that includes also, what's the probability of having a z-calc of 1.455 or greater, or negative 1.455 or below. So in order to do that, what we're going to do is we're going to take the right tail probability and we're going to multiply it by 2, equals the right tail probability multiplied by 2. And so because the probability of having z-calc or greater, so p equals 0.07 to 835, and same thing over on the other side. So if I come over here, so you got your probability over here on the left side, then you've got your probability over here on the right side, and so the probability of having a z-calc that's more extreme than 1.455 is actually the two of these probabilities added up together, which gives you 0.0145669. So we're going to come right back here, and we are going to just round that to 0.1457. So a p-value of 0.1457 is what we've got. And I've also got that already written down here. Why? Because I don't know why it's taking me so long to type all those numbers in. I just want it to copy and paste it. So the next thing that we do, so we found the probability. This is the probability of getting a z-value of this or more extreme. Now what we're going to do is we're going to say, hey, is this statistically significant? Is the result that we get, is it statistically significant? And in order to determine that, what we're needing to do is compare the p-value to the alpha value. So if the p-value is more extreme or less than the alpha value, then we're going to say that it is statistically significant. But if the p-value is greater than the alpha value, then it's not statistically significant. And in this case, the p-value of 0.1457 is not less than the alpha, or the probability of type 1 error. So therefore, what is our interpretation? What is it that we're going to say? Since the p-value is greater than the alpha, it's not statistically significant, like I said. So the probability of having a difference of 1,600 or more extreme between company A salary and company B salary, assuming that the null hypothesis is true, is 0.1457. So that's what we're writing right there. The probability of having that difference or more extreme, which could be, a difference of, that's an absolute difference, a difference of 1,600 or more, or negative 1,600 or less. And so that's what that looks like. It's just a difference. So what is your decision? Tell me whether you reject or fail to reject the null. So what we're doing is we fail to reject the null hypothesis, and we are doing this because we are comparing the z critical value to the z calculated value, right? And because the z critical value, because the z calculated value is not as extreme as, or is not more extreme than the critical value, we're not going to reject the null. And so we fail to reject the null hypothesis and are unable to demonstrate that there is a difference between company A and company B salary because the z calculated value of 1.45 is not beyond the z critical value of plus or minus 1.96. Okay, so now what we need to do is interpret our results in such a way that we would tell our boss, because that's what's important, right? If we don't know how to communicate it, really, what are we doing? So we are not able to demonstrate that there's a difference. Straight up, there's no we can't say that there's a difference. Is there a difference? Yes, there is a difference, but we can't really actually say that there's enough, information or proof to demonstrate that there truly is a difference. So we're not able to demonstrate that there's a difference in salaries between company A and company B with the present information that we have. Company A's salary average is 1,600 less than Company B's salary average. The probability of having a difference of 1,600 between Company A salary and Company B salary, assuming the two companies are the same, is about 14.57%. So that's how you would write that up. Just because there appears to be a difference doesn't mean that there actually is a difference. You need to write these. You need to go through the testing process to make sure whether or not there truly is a difference, and with how much confidence, how much proof do you have to be able to show that, or else you get that fun little thing called type 1 error when you say that there's a difference, but there really isn't a difference. So hopefully this was beneficial, and